Lesson 6.2, the ideal gas law and kinetic theory. The coefficient of expansion, notice, was the same for most gases. At low densities, gas molecules are far apart, so they don't really interact much. So that allows them to all behave approximately the same way. So we have this ideal gas law. Most gases are not perfectly ideal, but most of them are close to being ideal. So it's PV equals NKT, where P is the pressure in pascals, V is the volume in meters cubed, N is the number of particles, K is Boltzmann's constant, 1.38 times 10 to the negative 23 joules per Kelvin, and T is your temperature in Kelvin. Large number of molecules. There are a large number of molecules in a sample, so it's convenient to have a unit for a large number of things. Well, that unit is a mole. It's actually called a gram mole, and it is the number of atoms of carbon-12 in 12 grams. And so the number of atoms per mole is 6.022 times 10 to the 23, which is called Avogadro's number, 6.022 times 10 to the negative 23 per mole. So to find the number of moles in a sample, you take the number of particles and divide it by Avogadro's number. The number of moles can also be found from the mass, where you take the mass of your sample and divide it by the molar mass. The molar mass is the same number as the atomic mass from the periodic table. The unit would be grams per mole. So you'll have to look up your periodic table and find the atomic mass. It's not the big number, it's the other one. So, for example, carbon is atom 6, but its molar mass is 12.01. So we could rearrange or rewrite the ideal gas law with using moles. P is still pressure, V is still volume, T is still temperature in Kelvin. But N now is the number of moles, and R is the universal gas constant, 8.31 joules per mole Kelvin. And that is Avogadro's number times Boltzmann's constant. All right, we discovered in fluids that PV is energy. Just to review that, P is force over area, and volume is area times distance. So PV is force over area, and V is area times the distance. It's the area of the base times the height. So the A's cancel, and you just have PV equals force times distance. Oh wait, that's work or energy. So that means the nRT or the nKT must be energy too, since PV equals that. N and K are just numbers, and so is the R. So that means T must be energy. So T is the average kinetic energy of the molecules. So they've worked this out. PV equals NKT, but PV also equals 1/3 times the number of molecules times the mass of one molecule times the average speed that it goes squared. You use some calculus to get that. Kinetic energy is 1/2 mv squared. So, if we rearrange the top equation, we can get that kinetic energy is also 3/2 kT. If we solve that for V, we get our average speed of a molecule is the square root of 3kT over m. I'd like to point out T is in Kelvin, and m is the mass of one molecule. Not all molecules will go at the same speed. Some are going faster, some are going slower. This just gives you the average. Notice a higher temperature means a higher speed. Since they're moving faster, they can move farther, they're further apart. Hence, linear or thermal expansion. As they get hotter, they're moving more, so they move further apart. Let's say an apartment has a living room whose dimensions are 2.5 meters by 4 meters by 5 meters. Assuming the air in the room is composed of 79% nitrogen and 21% oxygen, at one temperature of 22 degrees Celsius and a pressure of, standard 1 atm, what is the mass of the air? Well, we could use, since we've got volume, and we've got pressure, and we have temperature, we could use the ideal gas law to find the number of moles of air. So it's PV, and we're going to use the nRT version. So our pressure is 1.01 times 10 to the 5 pascals. Our volume is 2.5 by 4 by 5. Looking for N. R is 8.31 joules per mole Kelvin. And our temperature, we need it to be in Kelvin. So add 273.15, and so our temperature in Kelvin is 295.15. Divide, and you find that the number of moles is 2060 moles. That's the N. That's the number of moles, but it's not the mass of the air. So to find the mass of the air, we could use that the number of moles is the mass of the gas over the molar mass. So N was 2060. The mass is what we're looking for. And our molar mass, well, we've got nitrogen. Nitrogen, from the periodic table, its molar mass is 14.0067 grams per mole. But it's N2, so there's two of those, so I'll multiply by 2. But it's only 79%, so I'll multiply by 0.79. So that's our nitrogen. And then we have our oxygen. Oxygen, on the periodic table, its mass is 15.9994 grams per mole. But again, there's two of those, and it's 21%. So I'm running out of space. You can calculate all that. Multiply the 2060 by the molar mass, and we get 59430 grams, or approximately 59.4 kilograms. That's about 131 pounds. It's a lot of air in there. Helium is a monoatomic gas, meaning that it floats around as free atoms. It fills a 0.01 meter cubed container. The pressure of the gas is 6.2 times 10 to the 5th pascals. So if there are 3 moles of gas, what is the temperature of the gas? Well, we could say PV equals, we know moles, let's use the nRT version. So our pressure is 6.2 times 10 to the 5th pascals. Our volume is 0.01 meters cubed. N is 3 moles. R, of course, has to be 8.31 joules per mole Kelvin. And we're looking for the T. So if you divide T is 249 Kelvin. All right, I'm going to clear the screen because I'm going to need the space to do this next one. All right, so what is the VRMS? Well, our VRMS, or root mean square speed, is found by the square root of 3kt over m. Well, I know the 3, the k, the t, but I don't know the m. The m is the mass of one helium atom. So to figure that out, I could say n equals m over the molar mass, n being the number of moles, but that's also the number of atoms over Avogadro's number. So I am looking for the mass. The molar mass of helium is 4.0026 grams per mole. I want one atom, and Avogadro's number is 6.022 times 10 to the 23 per mole. So if we multiply by the 4.026, that would give us 6.65 times 10 to the negative 24 grams. But the base unit for mass is kilograms. We need to make it kilograms. And now we know everything to find our root mean square speed. K, Boltzmann's constant, 1.38 times 10 to the negative 23 joules per Kelvin. T, we found in first part, was 248.7 Kelvin. And the bottom should be 6.65 times 10 to the negative 27 kilograms, which gives us 1,244 meters per second, going really fast. Should be, if I go perfect number significant figures, 1,200 meters per second, because there's 2 significant figures. So, ideally, you should be able to answer these questions. Have a good day.